In the hush before any star kindles, in a universe without light or dust or memory, quantum tremors breathe on the fabric of space-time, and inflation lifts them outward faster than any signal can follow, turning subatomic jitter into broad, faint undulations that will later guide the scaffolding of everything. A single field, named only for its duty, slides down a shallow potential, while its nearly constant energy drives an almost exponential swelling. Space doubles and doubles again, on the order of 60 e-folds, and wavelengths that begin smaller than an atom are carried beyond the causal horizon where they pause, their phases no longer able to coordinate, their amplitudes set like impressions in cooling glass. Only a fraction of a second sets the agenda for billions of years, a dry arithmetic the universe keeps without emphasis. The outline is austere. Vacuum fluctuations become classical curvature perturbations when expansion outruns their communication, and the spectrum they leave is nearly, but not exactly, scale invariant. A gentle red tilt away from perfect flatness that later maps will recognize. The statistics are simple in first view. The pattern is almost perfectly Gaussian, so the earliest irregularities read like a random field with no favored directions, only a stippled quiet of slightly more and slightly less. Inflation comes to its end when the field's stored energy relaxes. Reheating follows, repopulating space with particles, and the hot plasma begins to behave as a coupled fluid, but the imprinted ripples persist, small deviations in density that gravity will patiently amplify. Photons hold baryons buoyant with pressure and ring them with sound, while dark matter, aloof from scattering, slips more directly toward the tiny gravitational wells. A single score, different steps, no haste. The larger superclusters will owe their existence to quantum noise, a quiet irony the sky never bothers to underline. A lesser-known fact waits far from these first instants, yet listens faithfully to their echo. At the Sun-Earth L2 point, a spacecraft turns with measured regularity so cryogenic bolometers can sweep the whole sky. Thin spiderweb absorbers and delicate thermistors are cooled to tenths of a Kelvin by cascades of helium and dilution stages, cold enough to register microkelvin differences in the afterglow of a beginning that was very hot. The coldest instruments read the echo of the hottest beginning. The contrast requires no flourish. When electrons and protons later prefer to bind, the plasma turns transparent, photons decouple, and the cosmic microwave background streams free, carrying a snapshot of the imprint, variations of only a few parts in 100,000, a map of seeds left by expansion too fast to witness. In that map sit acoustic peaks at characteristic scales, the fossil of sound waves that swelled and stalled before transparency, and in that map sits the predicted soft tilt of slow roll dynamics, a spectral index modestly below unity that says the field did not linger on a perfect plateau. No drama announces any of this. The mathematics is patient. Hubble friction steadies the field's roll. Modes cross the horizon when their physical wavelength outgrows the causal scale. Once outside, their amplitudes effectively freeze like ripples captured beneath a skin of ice, and when they later re-enter, they return as instructions for structure. Observations speak in the same register. Time-ordered detector streams trace rings and great circles. Algorithms turn them into temperature maps. Maps become an angular power spectrum whose lowest multipoles and high L damping tail read like an accountant's ledger. From that ledger, the universe appears spatially near flat. The perturbations nearly Gaussian, the amplitudes small yet sufficient. Only a few microkelvin of contrast set the stage for all later glare. The mystery remains, quiet and unembarrassed. What precisely is the field that drove the swelling, and what shape does its potential truly take? Models arrive in families, plateaus and valleys, monomials and broken lines, fitted to the data rather than drawn from a device. The details of reheating, the coupling of the field to the species it must create, and the possible birth of a background of primordial gravitational waves sit in margins that tighten with each sky survey and still refuse to close. Non-Gaussianities remain small enough to be close to absent, which is itself a clue, but not a name. If an image is needed, it is a modest one, a hidden loom operating before there is cloth, drawing threads into being and setting their tension before any pattern is visible, or frost beginning at invisible specks, its branching lines deciding where later droplets will bead. The analogies admit their limits and stand aside. Inflation mends earlier puzzles with the same mild manner. Regions now far apart once shared a neighbourhood, so their near-identical temperatures require no coincidence. Curvature is ironed thin, so triangles behave as expected on the larger scales. Exotic relics that might have crowded the young cosmos are diluted into irrelevance by the very swelling that writes the seeds. The outcome is not theatrical, but sufficient, a nearly uniform universe that carries a precise, faint roughness. After inflation, expansion loses its sprint and keeps its walk. Sound waves run a limited course in the Baryonphyton fluid until transparency halts them. The microwave background departs on its long journey. Dark matter continues its quiet fall, beginning the slow task of turning tiny advantages into deep potential wells. It will be hundreds of millions of years before the first stars light the densest nodes implied here, longer still before filaments gather galaxies into rivers and clusters into heavy halos. Only took a sliver of early time to outline that calendar. Nothing here seeks applause. A nearly scale-invariant spectrum with a slight red tilt, a Gaussian random field, an upper limit on primordial tensor modes that keeps the loudest possibilities at bay, statements made in the syntax of calm, leave room for later chapters while fixing their coordinates. In that quiet, the invisible lattice is already implied, places where matter will have a head start, voids where it will not, threads laid by expansion itself. Heads bow to the simplicity of the rule, amplify the small, preserve the sign, and give gravity enough time. From this, everything else follows, and the universe proceeds as if it always intended to be ordinary in its beginnings and elaborate in its consequences. In the deepening quiet after the glare of recombination fades, the universe is filled with a nearly uniform bath of photons, a dilute gas of neutral hydrogen and helium, and the vast invisible ocean of dark matter that neither scatters nor shines. In this calm expanse, the faint density ripples imprinted during inflation begin their slow transformation into the scaffolding of all future structure. Gravity acts impartially, but dark matter, unburdened by the photon pressure that still ripples through baryons, slips ahead in the race toward the earliest clumps. These are not objects in the sense of stars or galaxies, but gentle overdensities. Their contrast only a few parts in 1,000, yet enough to deepen imperceptibly over cosmic time. Where the density is higher, dark matter's pull grows a fraction stronger, and the feedback is quiet but relentless. More matter falls in, the well deepens, and the flow becomes more decisive. It is an irony of cosmic history that the most influential structures form without ever emitting a single photon, their growth hidden entirely from direct sight. The baryons, still feeling the aftershocks of the primordial sound waves, lag behind, bound to the photon-baryon fluid's oscillations, until the universe cools enough for them to fall freely. The scale of these early dark matter wells is set by the physics of the hot plasma epoch. Free-streaming lengths, damping scales, and the sound horizon mark the size of the smallest and largest structures to form first. The smallest clumps may hold masses comparable to planets, but they are dark and silent, merging into larger hosts over billions of years without leaving any luminous fossils. A lesser-known fact rests in the modelling. When cosmologists simulate these early stages, they often represent dark matter as an enormous number of pseudoparticles, billions of them, each tracing the evolution of a much larger mass of matter than any star will ever contain, their positions and velocities stepping forward in cosmic time under Newton's law in an expanding frame. On the larger scales, the pattern emerging is one of delicate enhancement. Peaks and troughs in the density field stretched into a three-dimensional web. The peaks begin to form halos, the gravitational seeds of what will be galaxies. The troughs widen into voids, and all of this occurs long before the first star ignites, a silent assembly line working in darkness for hundreds of millions of years. One of the mysteries that persists even here is the precise nature of the dark matter particles themselves. If they are cold and massive, they clump readily on small scales. If they are warmer and lighter, free streaming can erase the tiniest structures, changing the later distribution of galaxies. Observations of the smallest galaxies today, the ultra-faint dwarfs on the outskirts of the Milky Way, act as fossil records for this early era, hinting at the scale below which structure never formed. In this period, the irony is that gravity is both the architect and the only witness. The interplay between dark matter and baryons remains asymmetric. Dark matter deepens the wells, baryons hesitate at the edges. The cosmic expansion continues to dilute both, but the overdensities resist the smoothing effect, their growth logarithmic in the radiation-dominated era, and linear after matter takes over as the dominant energy component. Around redshift 30, when the universe is only 100 million years old, the deepest wells begin to pull baryons inward in earnest, setting the stage for the epoch of reionization that will come much later. The analogy, if one is needed, is of a landscape where the valleys are dug in total darkness, and the rivers that will fill them have not yet begun to flow. Even now, the geometry of the future is being set. The spatial correlation function of the density field, a statistical measure of how matter is distributed, shows a faint bump at the scale of the sound horizon, a fossil imprint from before recombination. This bump will later be visible in the galaxy distribution as the baryon acoustic oscillation feature, a quiet ripple in the vastness of the cosmic web, telling of a time when matter and light moved together. Observationally, none of this can be seen directly in the early universe, but its fingerprints are abundant in the later sky. Galaxy surveys stretching billions of light-years outward map the evolved form of these first seeds. Gravitational lensing of the cosmic microwave background reveals the integrated effect of their growth. Even the statistics of galaxy cluster masses today depend on the amplitude of these early dark matter fluctuations, yet the true mechanism by which dark matter particles first assembled remains veiled. Were they born cold, heavy and slow-moving, as in the canonical WIMP scenario, or were they lighter, feebler, and produced in an earlier decay? This uncertainty keeps the narrative open-ended. Still, the evolution obeys a simple rule. Small clumps merge into larger halos, a process both chaotic in detail and orderly in the statistics it produces. Merger trees can be drawn for any given halo, showing how it grew by swallowing others over cosmic time, but the underlying dark matter remains unseen, traced only by the luminous matter that will later fall into its potential. A soft irony lingers here. The baryonic universe, with its stars, planets and observers, forms only within the boundaries set by something it cannot detect directly. The growth of these halos marks the beginning of nonlinear structure formation, but the large-scale pattern remains similar to its initial shape, merely amplified in contrast. Filaments begin to connect these halos, thin bridges of dark matter that will later guide the infall of galaxies. Voids expand between them, emptier than the cosmic average. Over time, the universe begins to resemble a sponge or a foam, with dense regions outlining vast cavities. Only took a few 100 million years to decide where the richest clusters and the emptiest deserts of space will be. The process is indifferent to scale. The same physics governs the fall of matter into a halo 1,000,000 light-years across, and into one the size of a dwarf galaxy's halo. The mathematics solutions to the collisionless Boltzmann equation in an expanding spacetime remains the same. Even here, long before any visible light from stars, the structure is already recognizably patterned, and the role of dark matter is already decisive. The silent dark has claimed the skeleton of the cosmos, and all luminous history will be written upon it without ever altering its shape. The invisible scaffold now extends across hundreds of millions of light-years, a network of subtle density enhancements that neither emit nor absorb light yet dictate the flow of all matter that will ever shine. In this era, as the universe cools further and the baryons finally fall freely without the pushback of photon pressure, the interplay between dark matter and ordinary matter begins in earnest, where the gravitational wells of dark matter halos are deepest. Baryonic gas streams inward along the same potential gradients, compressed and heated as it falls. The shapes of these wells are set by the cumulative infall of dark matter particles, cold, collisionless, and content to pass through one another without scattering, so their cores are diffuse and extended rather than sharply peaked. A quiet irony lies here. While gravity ensures that matter gathers, the absence of collisions means dark matter does not dissipate energy like gas does. It cannot form disks or settle into compact luminous structures, only remain as vast halos surrounding whatever baryons can condense in the center. The large-scale architecture begins to sharpen into filaments, thread-like concentrations of mass-connecting nodes where multiple filaments intersect. The nodes are the sites of the most massive halos, the precursors of galaxy clusters. Filaments themselves act as conduits, funneling gas and smaller halos toward these hubs. Simulations of this period show a striking resemblance to terrestrial networks. River basins draining into seas, capillaries feeding into veins. But the flow here is dictated solely by gravity, indifferent to direction or terrain, sculpted only by the original pattern of density fluctuations. A lesser-known fact emerges from such simulations. The cosmic web's filaments are not simple cylinders of mass, but exhibit complex internal flows, with material moving both along and perpendicular to their spines, a dynamic choreography invisible to any telescope. By now, redshift has fallen into the range of 20 to 10, corresponding to ages of about 200 to 500 million years after the Big Bang. The first stars will soon ignite within the densest baryonic cores of these halos, but the dark matter halos themselves have been growing quietly for much longer. Some halos at this stage have masses exceeding 1 billion solar masses, enough to bind gas so tightly that will resist being blown away by the energetic feedback from the first supernovae. Others remain small and fragile, easily stripped of gas by the ionizing radiation that will soon pervade the intergalactic medium. The irony here is that the strength of a halo's gravitational pull is determined by matter that will never participate in the chemical processes of star formation. Yet without that pull, the baryons would never have been able to gather to such densities at all. Observationally, this stage is far beyond direct imaging. No light from these halos reaches us unaltered, and the intergalactic medium is still largely opaque to certain wavelengths. The 21 centimeter spin-flip transition of neutral hydrogen, redshifted into the meter range, offers a potential probe. Fluctuations in its intensity trace the distribution of gas, which in turn follows the dark matter wells. Experiments like LOFAR and the SKA aim to map this signal, seeking indirect confirmation of the web's growth before galaxies made it visible. The mystery remains that, while the shape and evolution of the cosmic web can be matched in detail by cold, dark matter models, we still have no laboratory detection of the particle responsible. Whether it is a WIMP, an axion, or something stranger, it behaves here with mathematical predictability, a contradiction that cosmologists have learned to live with. As structure grows, the motions within halos and filaments become more complex. Mergers are common. Two halos approach along a filament, their relative velocities determined by the pull of the larger scale overdensity around them, and when they pass through each other, the dark matter components interpenetrate, while the baryonic components collide and shock, losing kinetic energy and settling deeper into the combined potential well. Over time, these mergers build up the mass of cluster-scale halos, each one a node in the network. The cosmic web itself expands with the universe, but its contrast sharpens. The dense regions grow denser, the voids emptier. In some ways, the evolution resembles the sharpening of a photographic negative, with the dark lines of filaments standing out ever more starkly against the pale background of near vacuum. Only took a few 100 million years of patient gravitation to carve the framework into which all luminous matter will be poured. A gentle modern analogy might be the steel frame of a building under construction, invisible beneath walls and floors when complete, yet determining the shape and strength of the whole. In the cosmic case, the frame will never be hidden from the point of view of gravity, but will remain forever invisible to light. As the first luminous structures ignite, they will appear exactly where the dark matter has prepared the way, a coincidence that is no coincidence at all. The filamentary network also defines the boundaries of the largest underdense regions, cosmic voids, whose diameters can exceed hundreds of millions of light-years. These voids are not empty in an absolute sense, but contain only a fraction of the average cosmic density, their expansion slightly faster than that of the universe as a whole. Dark matter in voids is too diffuse to gather baryons into galaxies efficiently, so these regions remain sparsely populated. The geometry of voids and filaments is statistical, but the pattern is recognizable at all epochs after this. Dense intersections, elongated bridges, and vast hollows, a structure arising naturally from the initial conditions and the nature of gravity. A lesser-known detail is that filaments and nodes also act as gravitational lenses long before any bright galaxies form within them, bending the paths of background photons in ways too subtle to measure now, but that will eventually contribute to the weak lensing signal seen in deep surveys. In this sense, the invisible network already casts shadows in the geometry of space-time, even before it is illuminated. By the end of this phase, the cosmic web is fully in place, though faint in its baryonic component. Gas is beginning to condense at the nodes, cooling via atomic transitions in hydrogen and helium, setting up the conditions for the birth of the first stars. Yet the layout, the great map of where matter will cluster and where it will thin, has been fixed for hundreds of millions of years, its design written in the language of initial density perturbations and amplified by the indifferent patience of dark matter's gravity. In the quiet arithmetic of cosmology, it will take billions more years to populate this scaffold with the spirals, ellipticals, and irregular galaxies we know, but the frame will change only in detail. The irony that endures is that the most permanent structures in the universe are those we can never see directly, guiding the evolution of everything visible while remaining themselves beyond the reach of light. The gravitational wells of dark matter halos now grow deeper as mergers and steady infall bring more mass into their reach, and baryonic matter, freed from the early photon pressure, begins to respond without delay, flowing along the invisible gradients set long before the first light. In the denser nodes where multiple filaments meet, the collapse is more rapid. Gas accumulates at the centers of halos, heating through compression, while dark matter continues to layer itself into extended halos whose radii can span hundreds of thousands of light years. These halos do not collide in the way gas clouds do. They pass through one another, their particles affected only by gravity, so their shapes and velocity distributions retain the memory of past encounters. A quiet irony is that in these invisible mergers, the most significant rearrangements of matter occur without any luminous sign to mark them, while the gas, shocked and heated by collision, will later produce the most visible displays. The web's filaments continue to funnel material inward, each stream carrying both dark matter and baryons toward the massive nodes. The gas within the filaments is tenuous, with densities far below those found in galaxies, yet its flow is steady over hundreds of millions of years, shaped by the gravitational pull of the web. Simulations reveal that these filaments are not static structures but dynamic channels, with coherent flows along their spines and slow accretion from their surroundings, feeding the nodes that will become galaxy clusters. A lesser-known fact is that the thickness of a filament, measured in megaparsecs, depends not only on the overall matter density, but also on the temperature of the intergalactic medium, which is set by the complex interplay of shock heating, cooling, and later feedback from the galaxies themselves. By redshift 10, roughly 500 million years after the Big Bang, the densest halos have reached the threshold where their baryonic gas can cool efficiently via atomic hydrogen transitions. This cooling allows the gas to lose pressure support and collapse further, forming dense clumps that will give rise to the first stars and stellar clusters. Yet even as this luminous era approaches, the underlying dark matter framework remains untouched by these processes. The identity of the dark matter particle still matters here. If warm dark matter were to replace cold, the smallest halos would have been suppressed, changing the abundance and distribution of early galaxies. Observations of the faintest galaxies in the local universe, satellites of the Milky Way and Andromeda, serve as relics of this formative time, offering indirect constraints on how the smallest dark matter structures formed. The slow assembly of the cosmic web also shapes the voids between filaments. These underdense regions are not merely empty spaces but expanding domains, their boundaries sharpened by the gravitational pull of the surrounding filaments. The irony is that the emptiest places in the universe are defined by the same gravitational physics that built the densest clusters. As voids expand slightly faster than the mean cosmic rate, they evacuate their interiors, pushing the sparse matter within toward their edges and subtly enhancing the density contrast of the web. This process too owes its scale and timing to the initial spectrum of density fluctuations and to the invisible hand of dark matter. The first halos massive enough to host galaxies form preferentially at the intersections of the thickest filaments. Gas flows inward, and in the centers of these halos cooling proceeds rapidly, enabling the collapse into dense protogalactic clouds. Stars will soon form here, but their locations, motions, and even their future interactions are already prescribed by the geometry of the dark matter network. A gentle modern analogy might be an unlit city grid laid out in full detail, before the first buildings rise or the first lights are switched on. The traffic patterns, the intersections, and the open spaces are all fixed, even if the visible city is years away. Observational cosmology can only approach this stage indirectly. Weak gravitational lensing, the minute distortion of background galaxy shapes by intervening mass, offers one route. By stacking and correlating these distortions across wide swathes of the sky, astronomers can infer the statistical properties of the dark matter distribution. Even at later times, the larger-scale lensing signal reflects the scaffolding established here. A lesser-known detail of weak lensing is that it is sensitive not only to the distribution of matter at a single epoch, but to the integrated mass along the entire line of sight, effectively giving more weight to the structures at intermediate distances between observer and background source. Thus, while we cannot see the dark matter filaments at redshift 10 directly, their descendants shape the weak lensing maps we make today. The mystery of the particle itself endures. Its invisibility to electromagnetic interactions allows it to slip unimpeded through baryonic gas, but its mass must be sufficient to seed structures on the smallest observed scales, and its behavior over cosmic time must match the power spectrum of fluctuations measured in the cosmic microwave background and in galaxy surveys, laboratory searches, whether in deep underground detectors shielded from cosmic rays or in accelerator experiments probing for new particles, have yet to yield a confirmed signal. Meanwhile, the cosmic web evolves exactly as if the cold dark matter model is correct, a contradiction that sharpens with each null detection. By the close of this era, the universe is on the verge of its first lights. The web's largest filaments are in place. The halos at their nodes are massive enough to bind gas against heating and dispersal, and the smallest galaxies are beginning to assemble in less massive halos. The cosmic geometry, set in place hundreds of millions of years earlier, is now poised to host the dramatic change from darkness to light. Yet the quiet force that shaped it all will remain unseen, holding the filaments taut and the nodes dense, ensuring that the luminous structures to come will never drift from their predetermined locations. It is a structure built not in haste, but with the patience of expanding space itself, a frame that will endure long after the brightest galaxies fade. The moment when light first pierces the cosmic darkness arrives in places chosen long before by the quiet gravity of dark matter. In the deep nodes where multiple filaments converge, baryonic gas has been cooling and condensing, losing its thermal support until the first dense stellar clusters ignite. These population 3 stars, massive and short-lived, burn hot and blue, their radiation intense enough to begin ionizing the surrounding hydrogen. Yet their positions, their proximity to one another, and even the scale of the regions they illuminate are dictated by the shape of the dark matter halos that cradle them. The irony is that the first visible transformation of the universe owes its pattern entirely to something that remains invisible. The halos hosting these first stars vary widely in mass. The smallest, just above the cooling threshold for molecular hydrogen, may only briefly sustain star formation before their gas is blown away by supernovae. Larger halos, with deeper gravitational wells shaped by more massive dark matter concentrations, can hold on to their gas and form subsequent generations of stars. The physics here is asymmetric. Dark matter continues to evolve solely under gravity, merging with other halos and accreting mass, while baryons must contend with heating, cooling, and feedback processes that can alter their trajectories and delay their assembly. Filaments act as supply lines, delivering fresh gas to these halos over tens of millions of years, and also bringing in smaller halos that merge to increase mass. Simulations of this era reveal that even the luminous bubbles of ionized hydrogen expanding around the first stars are not randomly distributed. They trace the filamentary skeleton of dark matter, clustering where the underlying density field is highest. A lesser-known fact is that the earliest ionized regions are highly aspherical, stretching preferentially along filaments where multiple sources contribute their radiation, and leaving long tendrils of partially ionized gas extending into the voids. As these first light sources fade and explode, they seed their surroundings with heavier elements, carbon, oxygen, silicon, created in their cores and spread by their deaths. But the dispersal of these elements follows the gravitational channels already established, funneled into the same filaments that guide gas flows. The cosmic web is not merely a map of where matter is, it is also a map of where the chemical evolution of the universe will proceed most rapidly. Observationally, direct detection of these earliest galaxies is beyond the reach of most current telescopes, but their integrated light contributes to the cosmic infrared background, and their ionizing influence is imprinted in the evolving optical depth of the cosmic microwave background photons as they traverse an increasingly ionized universe. The timing of this reionization is constrained by both these CMB measurements and by the appearance of the Gunn-Peterson trough in quasar spectra at later epochs, marking the end of the neutral phase. The role of dark matter during this luminous dawn remains as crucial as before. The smallest halos, which would be abundant in a cold dark matter scenario, can be suppressed if the dark matter is even slightly warm, altering the progression of reionization. This dependence makes the study of the early galaxy luminosity function a potential probe of dark matter's particle nature, though disentangling it from the effects of baryonic feedback is challenging. Mergers between halos during this period are frequent, especially in the dense nodes where filaments intersect. Each merger increases the depth of the gravitational potential, allowing more gas to cool and collapse, but also triggering bursts of star formation whose feedback can heat and expel gas temporarily. Dark matter itself is unaffected by these processes, retaining the memory of every merger in the substructure of the resulting halo. A quiet irony is that while dark matter determines the rate and geometry of mergers, the luminous signs of these events, starbursts, tidal features, disrupted morphologies, are entirely products of the baryonic component. The cosmic voids, by contrast, remain almost untouched by this new light. They expand and empty further, their dark matter content too diffuse to anchor significant baryonic collapse. In these regions, reionization proceeds last, driven by radiation leaking in along the filaments. The topology of reionization is thus an inside-out process, beginning in dense, dark, matter-rich nodes and advancing toward the low-density voids. A modern analogy might be a city's streetlights flickering on at dusk, with the brightest intersections illuminated first, and the empty outskirts lit only after the glow spreads outward. By redshift 6, roughly 1 billion years after the Big Bang, most of the intergalactic hydrogen is ionized, and galaxies are commonplace in the densest regions. Yet the structure of their distribution remains a scaled version of the underlying dark matter web. Clusters of galaxies correspond to the largest nodes, linked by chains of groups along the filaments, with the voids between them stretching vast and empty. Weak gravitational lensing surveys at later times will trace this pattern directly, confirming the match between luminous structure and dark matter distribution. A lesser-known observational technique, intensity mapping of spectral lines such as the 21 cm line of hydrogen or the rotational transitions of carbon monoxide, offers the promise of mapping the large-scale structure without resolving individual galaxies, potentially revealing the filamentary network even in these early epochs. The mystery that persists is how exactly the smallest scales within halos evolve under the combined influence of dark matter's gravity and baryonic processes. Feedback from star formation and black hole growth can expel gas from the central regions, temporarily reducing star formation efficiency. Yet the dark matter halo remains, continuing to accrete mass and to influence the flow of baryons back into its potential well. In this way, the invisible component provides long-term stability to structures that would otherwise be more easily disrupted. As the first billion years draw to a close, the cosmic web is both ancient and young. Ancient in the sense that its geometry has been in place since the earliest density fluctuations were frozen in by inflation. Young in the sense that the luminous structures that trace it are still forming and evolving. The enduring irony is that while the universe has transitioned from darkness to light, the agent that made this possible remains unseen, its presence inferred only from the patterns it shapes and the motions it governs. The filaments continue to feed the nodes, the voids continue to expand, and the stage is set for the grand assembly of galaxies, clusters, and superclusters that will define the universe for billions of years to come. The young universe, now threaded with luminous galaxies, shows its structure more clearly, but the underlying dark matter web is still the primary architect of its form. Each galaxy is embedded within a dark matter halo, whose mass outweighs the visible stars and gas by factors of 5 or more. The halo's gravity holding the system together and dictating its rotation and stability. Spiral galaxies spin too quickly for their visible mass alone to bind them. The unseen halo surrounding them extends far beyond the luminous disk, and it is this mass that keeps their outer stars from drifting away. This quiet fact, confirmed in the 20th century through the study of galaxy rotation curves, is one of the earliest direct signs of dark matter's pervasive influence. In clusters of galaxies, the effect is even more pronounced. The combined mass of the galaxies and the hot intracluster gas accounts for only a fraction of the gravitational pull needed to keep the cluster bound at the observed velocities. The rest lies in the extended dark matter halo that envelops the cluster, a structure whose profile has been shaped by countless mergers of smaller halos over billions of years. These mergers, still ongoing, leave the dark matter largely unaffected by collisional processes. Its distribution is altered only by gravity, so the final halo retains a record of its assembly history in the form of subhalos, smaller concentrations of dark matter that once hosted individual galaxies before being absorbed into the larger system. The irony is that while luminous matter within a cluster is subject to ram pressure stripping, shocks, and heating, the dark matter component remains unaltered by such interactions, its shape and extent determined solely by the geometry of the gravitational potential. Observational evidence for this comes not only from galaxy motions but also from gravitational lensing. The bending of light from more distant background galaxies reveals the projected mass distribution of clusters, allowing astronomers to map their dark matter halos directly. A lesser-known detail is that strong lensing events, where multiple images or arcs of a background galaxy are formed, often occur near the dense nodes of dark matter in the cluster's core, while weak lensing, a subtler statistical distortion, traces the extended halo to far greater distances. The Bullet cluster, a particularly famous case, offers a striking view of dark matter's separateness from baryonic matter. In the collision of two clusters, the hot gas component, visible in X-rays, lags behind due to pressure, while the dark matter halos, detected via lensing, pass through each other with minimal interaction, aligning instead with the galaxies that move ballistically through the collision. This separation is considered one of the clearest pieces of evidence for the existence of dark matter, contradicting theories that would attribute all gravitational effects to modifications of Newtonian dynamics alone. Filaments between clusters continue to feed them with fresh material, a process visible in simulations as thin streams of matter bridging the gap between massive nodes. These filaments contain both dark matter and diffuse gas, with the gas sometimes detectable through the Sunyaev-Zeldovich effect, where cosmic microwave background photons gain energy by scattering off hot electrons in the filamentary medium. Yet the dark matter component remains invisible, revealed only through its gravitational effects. The large-scale pattern is remarkably consistent with predictions from the initial conditions measured in the cosmic microwave background. The peaks in the early density field have grown into clusters, the ridges into filaments, the troughs into voids. The voids themselves are vast and still expanding, their interiors so underdense that galaxies are rare, and when present they are often low-mass systems with modest star formation. The gravitational influence of the surrounding filaments subtly shapes the motion of galaxies within voids, pulling them toward the walls and filaments over timescales of billions of years. A quiet irony is that even in emptiness, dark matter's presence is decisive. It is the absence of sufficient dark matter density that defines the voids in the first place. On scales of hundreds of millions of light-years, the cosmic web appears static to the human eye, but in reality it evolves continuously. Clusters merge along filaments, substructures fall inward, and the web as a whole grows more contrasted. The dense regions become denser, the empty regions emptier. Simulations tracking this evolution match the observed distribution of galaxies when the correct cosmological parameters are used, confirming the cold dark matter paradigm on these scales. Yet the particle physics of dark matter remains unknown. Candidates such as WIMPs, axions, and sterile neutrinos each imply subtle differences in structure formation on small scales. But disentangling these from the effects of baryonic physics, supernova feedback, active galactic nuclei, and gas cooling remains a challenge. A lesser-known fact is that some of the most sensitive tests of dark matter models come from gravitational lensing on small angular scales, where the presence or absence of subhalos affects the way light from background sources is distorted. In principle, these observations could rule out certain dark matter models, but the measurements require extraordinary precision. As the universe ages past a few billion years, dark energy begins to exert a stronger influence on the expansion, slowing the growth of large-scale structures. Gravity still pulls matter into clusters and along filaments, but the accelerating expansion reduces the rate at which new structures form. The existing cosmic web remains, but its growth is asymptotically frozen, the pattern becoming a kind of fossil of earlier epochs. The irony is that the same dark energy that will one day render most of the universe's galaxies unreachable to us also ensures that the dark matter web we see today will persist in its overall shape for trillions of years. Within this web, galaxies continue to evolve, but always within the confines of the halos and filaments laid out by dark matter. Even at the level of individual galaxy dynamics, the influence of dark matter remains dominant. The flatness of rotation curves, the stability of thin disks against disruption, and the binding of extended gas reservoirs all depend on the unseen halo. Without it, galaxies would be more fragile, more transient, and less able to survive interactions. In clusters, the same is true on larger scales. Without the binding mass of the cluster's dark matter halo, the high velocities of member galaxies would disperse them rapidly. Instead, they remain bound in systems containing thousands of galaxies, their motions governed by a gravitational potential dominated by the invisible component. Thus, even as our observations become more detailed and our simulations more precise, the basic fact persists. Dark matter determines the architecture of the universe on every scale above the smallest star-forming clouds. It is the hidden frame that holds all luminous history in place, indifferent to the light it enables. The vast filaments of the cosmic web, now fully adorned with luminous galaxies, remain dominated in mass and shape by their dark matter cores. These elongated structures act as the highways of cosmic evolution, guiding the motion of galaxies, groups, and gas toward the denser nodes where clusters grow. Within each filament, the gravitational field is not uniform. Subtle variations in the density of dark matter create local gradients that direct the flow of matter toward specific junctions. Over hundreds of millions of years, these flows build the mass of clusters, while simultaneously thinning the filaments themselves, an exchange that leaves the large-scale pattern intact but continually shifts material inward. Observations of this process are indirect but compelling. Galaxy redshift surveys reveal the large-scale anisotropy of galaxy positions, mapping filaments and their orientations across hundreds of millions of light-years, while weak gravitational lensing studies trace the smooth, extended distribution of mass along the same axis. The baronic component in filaments is faint, often detectable only through subtle signals such as the thermal Sunyaev-Zeldovich effect or faint X-ray emission from shock-heated gas, but these luminous traces sit within the far more massive dark matter backbone. A quiet irony is that the most massive structures in the universe are not the brightly lit clusters themselves, but the dim, extended filaments that connect them, their total mass dominated by something we cannot see. The internal kinematics of galaxies within filaments also bear the imprint of dark matter. Their peculiar velocities, departures from the smooth Hubble expansion, reflect the gravitational pull of both the filament and the clusters it feeds. This motion creates measurable redshift space distortions, compressing or elongating the apparent structure along the line of sight depending on the observer's perspective. A lesser-known fact is that such distortions are used not only to study the growth of cosmic structure, but also to test models of gravity, with the results consistently matching the expectations from general relativity combined with cold dark matter. Within the densest filaments, smaller halos and their galaxies fall toward larger ones, engaging in minor mergers that steadily increase mass. These events are frequent but less dramatic than the major cluster-cluster mergers at the nodes. They add structure without significantly disrupting the overall filament. The smoothness of dark matter's gravitational influence ensures that these accretion flows are coherent over vast distances. Even the most massive clusters, anchored at the intersections of several filaments, owe their continued growth to this steady, quiet supply of material. Simulations suggest that the geometry of the web, its connectivity, the number of filaments meeting at a node, affects the morphology and evolution of the galaxies within. Nodes with many connecting filaments tend to host richer clusters, and the galaxies arriving along each filament may retain directional coherence in their angular momentum, imprinting a subtle memory of their infill path onto their rotation. The mystery of dark matter's identity becomes even more acute when studying the internal structure of filaments. While their large-scale form matches cold dark matter predictions well, the small-scale clumpiness, how smooth or grainy they are, depends directly on the particles' free-streaming length and interactions. Warm dark matter models would produce smoother filaments with fewer subhalos, while cold dark matter allows a hierarchy of structure down to extremely small masses. Current observations cannot yet resolve these differences in filaments, leaving the question open. As cosmic time advances past several billion years, dark energy's accelerating expansion begins to slow the growth of the web. Filaments lengthen, and their density contrast with the background continues to increase, but the infall rate of new material declines. Clusters reach a point where most of their future mass is already in place, their surrounding filaments becoming less effective supply lines. The irony here is that the structures that took billions of years to assemble will persist for trillions more, frozen by the expansion into near-permanent configurations, yet the active growth phase will occupy only a small fraction of cosmic history. Observational campaigns targeting the cosmic web at intermediate redshifts, between about 1 and 3, capture it in this period of peak activity. Deep galaxy surveys, combined with lensing and Sunyaev-Zeldovich maps, reveal filaments stretching tens of megaparsecs, often with embedded groups and small clusters acting as waypoints along the route to massive nodes. A lesser-known observational method, the absorption of quasar light by intervening intergalactic gas, also traces filaments indirectly. The so-called Lyman alpha forest, a dense thicket of absorption lines in quasar spectra, maps fluctuations in the density of neutral hydrogen that align closely with the underlying dark matter distribution. The connection between luminous traces and the invisible web is not perfect, shaped by the complexities of baryonic physics, but the large-scale agreement is strong enough to confirm the gravitational framework. Within the filaments, star formation proceeds at a modest rate compared to the starbursting nodes, but the galaxies there are often less disturbed by interactions, allowing them to retain extended gas disks and steady rotational patterns. Still, their future is tied to the inexorable pull of the web. Over cosmic time, most will migrate toward denser regions, merge into larger systems, or be stripped of their gas during passage through the hot intracluster medium. Even the most isolated galaxies cannot escape the geometry laid out by dark matter. The voids between filaments, now vast and nearly empty, continue to expand, their influence felt at the edges where low-density matter is drawn toward the surrounding walls. Some simulations suggest that galaxies in void interiors may experience slower evolutionary paths, with lower star formation rates and fewer mergers, but they remain gravitationally connected to the web at large through the sparse dark matter that permeates even these emptiest regions. By the present epoch, the cosmic web is both a dynamic structure and a relic. Its formation, guided by the invisible hand of dark matter, reflects the initial conditions of the universe with remarkable fidelity, while its ongoing evolution is shaped by the balance between gravity's pull and the accelerating expansion of space. The filaments still carry galaxies and dark matter toward clusters, but at a diminishing rate. The nodes still grow, but more slowly, and the voids still widen, their interiors destined to become ever more isolated. The enduring irony is that the grandest visible structures in the universe, the chains of galaxies, the luminous clusters, the glowing bridges of gas, are secondary features of a framework built entirely of matter we cannot detect directly. A framework that has been in place since the universe was less than 1% of its current age. In the stillness of cosmic time, that framework remains the quiet engine of structure, unseen yet inescapable. In the largest nodes of the cosmic web, the assembly of galaxy clusters reaches its peak, and the scale of these structures reveals the full extent of dark matter's influence. Each massive cluster contains thousands of galaxies bound together by a gravitational potential dominated overwhelmingly by dark matter, with the luminous galaxies and the hot intracluster gas accounting for only a small fraction of the total mass. The halos of these clusters extend for several megaparsecs, their density profiles following the form predicted by simulations of cold, collisionless matter, with dense cores and long, diffuse outskirts that blend into the surrounding filaments. The galaxies within move at velocities of hundreds to over 1,000 kilometers per second, speeds that would fling them into intergalactic space if not for the vast dark matter halo holding them in place. The hot gas filling the space between galaxies in a cluster reaches temperatures of tens of millions of degrees, emitting X-rays. But this luminous plasma is not the primary mass component. It is merely the visible filler within an invisible framework. A quiet irony is that the gravitational lensing caused by the cluster's dark matter can reveal background galaxies more clearly than the galaxies within the cluster itself, magnifying and distorting their light into arcs and multiple images. The lensing maps show that the mass distribution in clusters does not perfectly follow the light, with dark matter peaks sometimes offset from the baryonic gas, especially in the aftermath of mergers. A lesser-known detail is that such offsets provide constraints on the possible self-interaction cross-section of dark matter particles. If dark matter interacted strongly with itself, it would behave more like the collisional gas during a merger, lagging behind the galaxies, but observations of systems like the Bullet cluster show minimal such lag, indicating that dark matter is largely collisionless. The internal substructure of clusters is rich with smaller dark matter halos, many of them hosting dwarf galaxies or remnants of past mergers. These subhalos preserve the memory of the cluster's assembly history, their orbits tracing the gravitational well in 3 dimensions. The hot intracluster medium interacts with galaxies passing through it, stripping gas from their disks in processes like ram pressure stripping, which quenches star formation, yet the dark matter halos of these galaxies remain intact long after the visible components are altered. This asymmetry underscores the independence of dark matter from baryonic processes, a theme constant throughout cosmic history. The filaments feeding the clusters remain active, though their supply has slowed under the influence of cosmic acceleration. These filaments deliver not just galaxies and dark matter, but also the hot and warm gas that maintains the intracluster medium, often entering at high velocities and generating shocks that are visible in X-ray and radio observations. Simulations reveal that the geometry of filamentary infall can influence the shape and orientation of the cluster's dark matter halo, sometimes producing elongated mass distributions aligned with the incoming streams. The mystery of dark matter's microphysical nature remains, but its macroscopic behavior here is well understood. It dominates the gravitational potential, defines the scale and density of the cluster, and shapes the motion of every luminous component. Observationally, gravitational lensing remains the most powerful direct probe of this dark matter distribution, especially when combined with X-ray mapping of the gas and spectroscopic measurements of galaxy velocities. Together, these datasets paint a consistent picture. The dark matter halo of a massive cluster is the deepest gravitational well in the present-day universe. On still larger scales, superclusters form as loose associations of clusters linked by filaments, but these are not gravitationally bound as single entities. The accelerating expansion of space will eventually pull them apart. The irony is that while dark matter bound the largest structures together for billions of years, it cannot counter the effect of dark energy on scales beyond the reach of their mutual gravity. In the far future, the clusters themselves will remain intact, their internal dark matter halos holding them together, but the filaments connecting them will thin and fade from view. A lesser-known observational challenge in studying the dark matter of clusters is the so-called mass-concentration relation, a scaling between the total mass of a halo and the concentration of its mass toward the center. Simulations predict a weak correlation, but measurements from lensing and dynamics sometimes find higher concentrations than expected, prompting debates over whether baryonic physics, projection effects, or new dark matter physics might be responsible. As clusters evolve, their cores can become sites of intense baryonic activity, cooling flows of gas, bursts of star formation in central galaxies, and the growth of supermassive black holes whose feedback can heat and stir the surrounding gas. Yet these processes, energetic as they are, affect only a small fraction of the cluster's total mass, and have little impact on the extended dark matter halo. The dark matter's slow, steady gravitational pull remains the dominant force shaping the cluster's fate, even in the most violent cluster mergers, where shock fronts race through the gas at supersonic speeds and galaxies are flung into new orbits. The dark matter passes through largely unimpeded, continuing to define the potential in which all else moves. By the present epoch, Some of the most massive clusters, such as those in the Coma or Perseus regions, have accumulated masses exceeding a quadrillion solar masses. These structures represent the culmination of the hierarchical growth process driven by dark matter. Small halos merging into larger ones, filaments feeding the nodes, and the cosmic web amplifying the density contrasts set in the first instance after inflation. Yet even at this scale, the halos are not smooth. They are laced with substructure, reflecting the detailed history of their growth. The ultimate irony is that despite their enormity, clusters are but the visible tips of dark matter over densities that extend far beyond their luminous edges, blending into the web and anchoring the largest coherent structures in the universe. As cosmic time stretches on, the story of these clusters will shift from growth to isolation. Dark energy will continue to accelerate the expansion, reducing the inflow from surrounding filaments until the clusters become gravitational islands in an ever emptier cosmic sea. But within their boundaries, the dark matter will continue to bind galaxies, gas and light, maintaining the shape of these massive systems for unimaginably long periods. In the stillness of the far future, when most of the cosmic web has thinned beyond recognition, these clusters will stand as enduring monuments to the organizing power of dark matter, a power that has worked in silence since the universe was young. The large-scale pattern of the cosmic web has now reached maturity, its filaments, clusters, and voids firmly in place, shaped by billions of years of dark matter's unbroken gravitational guidance. On the scale of hundreds of millions of light-years, the geometry is strikingly consistent with the imprint of the primordial density field measured in the cosmic microwave background, an enduring reminder that the scaffolding for this vast network was established when the universe was less than a second old. The filaments remain the principal channels of matter transport, slowly moving galaxies, groups and streams of gas toward the massive nodes. Within these filaments, dark matter dominates the mass budget, its distribution setting the precise locations where smaller halos merge, where galaxies align, and where clusters continue their slow growth. Observations at this scale rely heavily on statistical reconstructions. Galaxy surveys provide a sparse sampling of the underlying density field, while weak lensing and the Lyman alpha forest fill in the invisible components. Together, they reveal that the luminous galaxies trace only the densest ridges of a far more extended dark matter spine. A quiet irony lies in the fact that the most massive, coherent structures in the universe, the great filaments, are not bound by their own gravity on the largest scales. They are transient in the cosmic sense, destined to thin and fragment under the influence of dark energy. Yet they have already determined the destinies of countless galaxies. Within the dense nodes, galaxy clusters continue to evolve through mergers, infall and internal dynamics. Subclusters fall in along specific filamentary pathways, their dark matter halos merging with the central cluster halo in complex multipass encounters. The luminous galaxies within these infalling systems often show evidence of tidal disruption, ram pressure stripping, and star formation quenching, while the dark matter components pass through with little alteration except for changes in their velocity distributions. A lesser-known fact is that in these mergers, the dark matter halo of the main cluster can exhibit oscillations in its potential well, a kind of gravitational ringing, as it absorbs the incoming mass, temporarily altering the orbits of member galaxies before settling again. The voids, meanwhile, have expanded into vast underdense regions spanning hundreds of millions of light-years. Their interiors contain only sparse dark matter and a handful of faint galaxies, often small, irregular, and isolated from major filamentary flows. These galaxies evolve slowly, with few interactions to trigger starbursts or morphological changes, The boundaries of voids, marked by thin walls and connecting filaments, are shaped almost entirely by the gravitational influence of the surrounding dark matter, which draws material outward from the void's interior while feeding it toward the denser regions beyond. The irony here is that the most rapid motions in the large-scale structure often occur at the edges of the emptier spaces, where the gradient in gravitational potential is steepest. The study of voids provides unique constraints on cosmology. Their shapes, sizes, and expansion rates respond sensitively to the balance of matter and dark energy in the universe. Mapping them requires large-scale galaxy surveys, and their alignment with the dark matter distribution is tested through simulations that evolve billions of particles under gravity alone, showing near-perfect agreement on these scales. In the intermediate density regions of the web where filaments meet smaller groups of galaxies, the dynamics are calmer. Here, dark matter halos of modest mass host galaxies with ongoing star formation, fed by a steady but limited supply of gas. These systems often retain thin disks, their rotation curves still rising toward the flat profiles characteristic of a dominant dark matter halo. The link between halo mass and galaxy morphology is not absolute, shaped as much by environment as by intrinsic properties, but the gravitational framework within which each galaxy evolves is always set by the dark matter halo it inhabits. On galactic scales, the evidence for dark matter remains unambiguous. Flat rotation curves, the dynamics of satellite galaxies, and the stability of extended gas disks all point to an invisible component outweighing the visible mass by a large margin. A lesser-known observational technique, stellar streams, tidal remnants of dwarf galaxies and globular clusters, provides a fine-grained probe of the Milky Way's dark matter halo. The shape and density variations in these streams reveal the underlying gravitational potential, including perturbations from dark subhalos that may be entirely devoid of stars. Detecting and characterizing such subhalos offers one of the most direct ways to test dark matter models on small scales, potentially distinguishing between cold, warm, or self-interacting varieties. The mystery persists, however, while the gravitational effects of dark matter are measured with increasing precision. No direct detection of the particle has been achieved in laboratory experiments or astrophysical observations. Underground detectors search for rare scattering events. Telescopes scan for annihilation or decay signatures, and accelerators probe for new particles beyond the standard model, but the results so far remain null. This disconnect between cosmological certainty and particle physics ignorance is one of the central puzzles in modern science. As cosmic time moves forward, the influence of dark energy becomes ever more pronounced. The expansion accelerates, stretching the voids and slowly reducing the rate at which matter flows along the filaments into the clusters. On the largest scales, the growth of structure effectively freezes, leaving the web as a near-static skeleton while the small-scale dynamics within clusters and galaxies continue. This transition marks a shift from a universe in which the balance of forces allowed new structures to form to one in which existing structures simply age within the framework already established. The irony is that the period of most vigorous growth, spanning only a few billion years, has set the conditions for a cosmic future lasting trillions. In this future, the observable universe will shrink as light from distant structures is red-shifted beyond detectability, but the dark matter halos of galaxies and clusters will remain intact, still shaping the motions of stars and gas within their reach. In the present epoch, we stand at a point where both the early and late phases of this grand structure are visible. The faint imprint of the first density fluctuations in the cosmic microwave background, the fully developed web traced by galaxies and gas, and the beginnings of the slow fade into cosmic isolation. Each of these phases bears the unmistakable signature of dark matter's gravitational influence. From the smallest satellite galaxies to the largest superclusters, from the internal kinematics of disks to the motions of clusters along filaments, the same invisible framework holds. And yet, despite decades of observation and simulation, the physical nature of the component that has shaped the universe remains hidden, as silent now as it was before the first star burned. On the scale of individual galaxies, the influence of dark matter is most directly felt in their rotation curves and velocity dispersions, signatures that reveal mass far beyond what is visible. In spiral galaxies, the measured orbital speeds of stars and gas remain flat or even rise at large radii, contradicting the expectation from Newtonian dynamics if only the luminous mass were present. The simplest and most consistent explanation is an extended halo of dark matter whose density declines more slowly than that of the visible disk, providing the gravitational pull needed to sustain these motions. This halo is not confined to the galactic plane. It envelops the galaxy in a roughly spherical or triaxial distribution, extending far beyond the regions lit by stars. The quiet irony is that the most stable, enduring component of a galaxy is the one that is never seen, shaping the visible structure without ever taking part in the luminous processes that define our idea of a galaxy. In elliptical galaxies, dark matter reveals itself through the velocity dispersion of stars and the gravitational lensing of background objects, both indicating far more mass than the starlight accounts for. Galaxy-galaxy lensing, where the weak lensing signal of many foreground galaxies is stacked statistically, maps the average halo profile and confirms the ubiquity of these invisible envelopes. A lesser-known detail is that these halo profiles often follow a form similar to the Navarro-Frank-White profile predicted by cold dark matter simulations, though deviations in the central regions, known as core cusp problems, have prompted debate about whether baryonic feedback or new dark matter physics might be responsible. In low surface brightness and dwarf galaxies, the effects of dark matter are even more pronounced. These systems have relatively little luminous mass, making their rotation curves dominated by dark matter at all radii. Because they are also more weakly bound, they are sensitive to tidal interactions with larger galaxies, and the stripping or distortion of their halos can be used to study the distribution of dark matter in both the satellite and the host. In the local group, the motions of satellite galaxies around the Milky Way and Andromeda provide constraints on the total halo mass of each, revealing that our own galaxy's dark matter halo extends at least a few 100,000 light-years from the center. Stellar streams from disrupted satellites such as the Sagittarius stream act as fine traces of the Milky Way's gravitational potential, and perturbations in these streams suggest the presence of dark subhalos that lack any stars, a possible direct imprint of the smallest building blocks predicted by the cold dark matter model. The mystery deepens here, because if dark matter is truly cold and collisionless, subhalos should be abundant, yet many have no detectable baryonic counterpart. This missing satellites problem has been a subject of intense research, with solutions ranging from feedback processes that prevent star formation in low-mass halos to alternative dark matter models that suppress the smallest structures. Observations with the Hubble Space Telescope and more recently the James Webb Space Telescope have begun to probe dwarf galaxies at greater distances and earlier epochs, providing a test of these ideas. The distribution of dark matter within galaxies also affects their long-term evolution. The halo's mass sets the escape velocity for gas driven out by supernovae or active galactic nuclei, determining whether the material is lost forever or falls back to fuel future star formation. In galaxy mergers, the dark matter halos interact gravitationally, slowing and binding the galaxies together long before their luminous components physically collide. Simulations show that the halos merge first, creating a combined gravitational well into which the baryons eventually settle, forming the remnant galaxy. A lesser-known fact is that the angular momentum of a galaxy's disk is partly inherited from the tidal torques experienced by its halo during early large-scale structure formation, meaning that the orientation and spin of visible disks still carry an imprint of the dark matter environment in which they formed. In galaxy clusters, the same principles apply on a larger scale. Each member galaxy's dark matter halo is embedded in the much larger cluster halo, and interactions between them can strip away outer halo material while leaving the dense inner regions intact. This stripping alters the subhalo mass function within clusters, another potential probe of dark matter physics. Weak lensing surveys of clusters reveal the statistical distribution of subhalo masses, and these results are compared against simulations to test whether the cold dark matter model holds at these intermediate scales. The results so far are broadly consistent, though uncertainties remain, especially regarding the impact of baryonic processes on subhalo survival. As the universe ages, galaxies and their halos evolve in an environment increasingly dominated by dark energy. The rate of mergers declines, and isolated systems become more common. In the far future, galaxies will remain bound to their halos, but the larger structures of the cosmic web will stretch beyond contact. The irony is that while dark matter is the reason galaxies formed at all, it is also the reason they will remain coherent long after most of the universe has receded from view. Observational programs continue to refine our understanding of galaxy-scale dark matter, from precision rotation curve measurements in nearby spirals to lensing-based mass maps in distant systems. Each new dataset strengthens the case for a pervasive non-luminous component whose gravitational influence is the dominant factor in shaping galactic dynamics. Yet despite the growing precision of these measurements, the nature of dark matter remains elusive. Laboratory experiments have not yet detected a convincing signal. Indirect searches have not yielded definitive evidence of annihilation or decay products, and collider experiments have not produced particles that match the necessary properties. This disconnect between astrophysical certainty and particle physics mystery defines the present state of the field. On every scale, from dwarf galaxies to massive clusters, the gravitational influence of dark matter is clear, yet the particle's identity remains hidden. The paradox is that the universe's largest structures and its smallest particle-scale mysteries are bound together by the same phenomenon, a phenomenon that continues to shape the cosmos in silence. On the grandest scales accessible to observation, dark matter's role in shaping the cosmic web is revealed most clearly through the statistical patterns of galaxy positions, mapped across billions of light-years. Redshift surveys such as the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument have charted the three-dimensional distribution of millions of galaxies, showing that they form an intricate network of clusters, filaments, and voids, whose geometry matches the predictions of cold dark matter cosmology with remarkable precision. The baryon acoustic oscillation feature, a subtle excess in the number of galaxy pairs separated by a fixed scale of about 150 megaparsecs, stands out in these surveys as a fossil of sound waves in the early universe's photon-baryon plasma, imprinted before recombination, and preserved in the clustering of matter by the gravitational dominance of dark matter. This feature provides a standard ruler for measuring the expansion history of the universe, linking the large-scale structure we see today with conditions in the first few 100,000 years after the Big Bang. The quiet irony is that this imprint of the earliest physics could not have survived without dark matter's stabilizing influence. Without it, baryonic matter alone would have been too easily washed out by photon pressure before decoupling. The large-scale clustering pattern also encodes the growth rate of structure over cosmic time, a quantity sensitive to both the amount and nature of dark matter and to the influence of dark energy. A lesser-known fact is that redshift space distortions, anisotropies in the apparent clustering caused by galaxy-peculiar velocities, allow astronomers to measure this growth rate directly, offering a test of gravity on cosmological scales. The results so far agree with general relativity combined with cold dark matter, but future surveys will tighten these constraints, possibly revealing deviations that point toward new physics. Weak gravitational lensing surveys, such as those from the Dark Energy Survey and the Hyper-Supreme CAM, map the projected mass distribution across large swathes of the sky by measuring the tiny coherent distortions in the shapes of millions of background galaxies. These maps trace both dark and luminous matter, revealing the same web-like pattern seen in galaxy surveys, but without the bias introduced by using galaxies as tracers. The lensing maps show that the matter density fluctuations match cold dark matter predictions over a wide range of scales, though some analyses suggest slightly less clustering than expected, a potential hint of new physics or unaccounted-for systematic effects. Cosmic shear, the statistical correlation of these lensing distortions across the sky, provides another way to measure the growth of structure, and its sensitivity to dark matter's role in that growth makes it a cornerstone of modern cosmology. In addition to these optical surveys, the cosmic microwave background itself offers a lensing signal. As its photons travel from the surface of last scattering, their paths are bent by the intervening large-scale structure, subtly distorting the observed temperature and polarization patterns. This CMB lensing maps the integrated mass along each line of sight, confirming that the same invisible web seen at lower redshifts extends back to the early universe. The mystery is that all of these independent measurements, galaxy clustering, baryon acoustic oscillations, weak lensing, CMB lensing, paint a consistent picture of a universe dominated by dark matter, yet they do not reveal what the dark matter is made of. Laboratory searches for weakly interacting massive particles have steadily improved in sensitivity, ruling out large swaths of parameter space once thought most promising, while searches for ultralight axion-like particles are probing new regions of possibility. Indirect searches for annihilation or decay products in gamma rays, neutrinos, and cosmic rays continue but have yet to find compelling evidence. In the absence of a particle detection, astrophysical observations remain the primary source of knowledge about dark matter, and they point to a component that is cold, collisionless, and non-relativistic at the time structures began to form. Simulations of the universe's evolution under these assumptions produce large-scale structures that match what we observe, including the correct abundance and distribution of halos, the connectivity of the web, and the statistical properties of voids. A lesser-known aspect of these simulations is that they can also reproduce the velocity field of galaxies, their flows toward overdensities and away from underdensities, providing yet another line of agreement between theory and observation. The irony is that while the overall framework works so well, small-scale discrepancies persist, such as the core-cus problem in dwarf galaxies, the too-big-to-fail problem in the most massive subhalios, and the exact abundance of satellite galaxies around systems like the Milky Way. These may reflect the complex effects of baryonic physics on dark matter distributions, or they may be clues to a more complex dark sector. As cosmic time advances further into the dark energy-dominated era, the growth of large-scale structure will slow almost to a halt. The filaments will thin, the supply of new material to clusters will dwindle, and the pattern of the cosmic web will freeze and move in coordinates. In trillions of years, Only the most local structures will remain gravitationally bound, while the rest of the web will fade beyond the cosmological horizon. Yet the dark matter within those bound systems will continue to govern their internal dynamics, ensuring that galaxies remain intact even as the universe grows cold and dark. The enduring irony is that the most enduring structures, the ones that will outlast all stars and all light, are those shaped and sustained by a form of matter that has never been directly seen, only inferred through its persistent pull on everything we can see. As the cosmic web enters its late evolutionary phase, the balance between the gravitational pull of dark matter and the accelerating influence of dark energy tilts decisively toward expansion. The filaments, once active channels funneling matter into clusters, now see their inflow rates decline, their outer reaches stretching and thinning under the persistent push of the expansion. Within gravitationally bound regions, however, dark matter's hold remains absolute. Galaxy clusters retain their mass and internal structure, their dark matter halos extending far beyond the luminous boundaries defined by galaxies and hot gas. These halos preserve the memory of past assembly, the infall along specific filaments, the mergers that built their cores, the subhalos that orbit within them like silent satellites. A quiet irony is that while the cosmic web as a whole will eventually disperse, the largest bound structures will remain locked in their present form for timescales that dwarf the current age of the universe. Inside these clusters, galaxies continue to interact and merge, often guided into the dense core by the gravitational drag of their dark matter halos. The process of dynamical friction, where the motion of a massive galaxy through a sea of dark matter particles creates a trailing over density that slows it, is one of the most efficient ways to bring galaxies together in the cluster environment. A lesser-known fact is that this mechanism operates over billions of years, ensuring that even in a slowing cosmic economy, the internal structure of clusters keeps evolving. Observations of galaxy distributions, intracluster light and lensing maps show that the dark matter density peaks often align with the concentration of galaxies rather than with the hot gas, a reflection of the differing physics that govern collisional baryons and collisionless dark matter. The hot intracluster medium remains a luminous tracer of the cluster's baryonic content, visible in X-ray emission and through the Sunyaev-Zeldovich effect, but it is gravitationally confined by a mass profile dominated by dark matter. In the outer regions of clusters, where the density drops toward the background level, the transition between bound and unbound matter marks the edge of the halo, a boundary that expands only slowly as the Hubble flow overtakes more distant material. Filaments that once fed the cluster with a steady stream of galaxies now deliver less and less, their cross-sections widening and their density contrast diminishing. Simulations show that the connectivity of the web, the number of filaments feeding each massive halo, declines over time, a measurable sign of the universe's transition into dark energy domination. The mystery of dark matter's nature remains as stark here as in the early universe. Its gravitational influence is mapped with exquisite precision by weak and strong lensing, but no laboratory experiment has confirmed the existence of the particle or particles responsible. Searches for self-interactions have so far yielded only upper limits, consistent with the view that dark matter is almost entirely collisionless. The bullet cluster and other merging systems continue to serve as benchmarks, showing the separation of dark and baryonic mass in action, with the dark matter distribution aligning with the collisionless galaxies rather than the collisional gas. In cosmic voids, the expansion accelerates their isolation. These vast regions, already underdense in both dark and luminous matter, become increasingly empty as their sparse contents drift towards surrounding filaments, A quiet irony is that the absence of dark matter here is just as significant as its presence elsewhere. Without enough mass to counter expansion, the voids grow faster than the mean universe, exaggerating the contrast between emptiness and density. This evolving geometry can be measured through surveys of galaxies and intergalactic gas, and its statistical properties offer constraints on cosmology independent of those from clusters and filaments. Within galaxies, the halos remain the primary regulators of structure and stability. In spirals, the flatness of rotation curves persists. In ellipticals, velocity dispersion profiles continue to trace the halo's mass. Satellite galaxies orbit within these halos on paths shaped by the combined potential of the host's dark matter and the larger scale environment. A lesser-known observational technique, timing the motions of satellite pairs or groups, provides independent estimates of halo masses, often confirming results from lensing and dynamics. On the smallest scales, the predicted abundance of subhalos in cold dark matter simulations still exceeds the number of observed luminous satellites. But deep surveys are gradually revealing more faint systems, closing the gap and suggesting that many low-mass halos may host only a handful of stars or none at all. As the accelerating expansion continues, the larger-scale growth of structure will freeze out entirely. The cosmic web will persist in co-moving coordinates, but in physical terms its components will drift beyond one another's reach. Clusters will become cosmic islands, retaining their galaxies, gas and dark matter, but no longer connected by active filaments. The internal evolution of these islands will proceed for trillions of years, with dark matter halos holding their structure against the slow attrition of baryonic processes. The irony is that the longest-lived structures in the universe's history will be those built on an invisible foundation we still do not understand. The legacy of dark matter is not only the architecture of the cosmos, but also the fact that this architecture will outlast almost everything else. Stars will burn out, gas will cool and fade, and the light from distant galaxies will vanish beyond the horizon, but the dark matter skeleton will remain, unseen yet intact, shaping whatever remains long after the luminous chapter of the universe has closed. In this late epoch, future observers, if any, will see a sky vastly emptier than ours, yet every motion of every surviving star and galaxy will still carry the imprint of dark matter's ancient silent work. In the cosmic present, the interplay between precise observation and theoretical modelling has refined our understanding of dark matter's role in structure formation, yet it has not lifted the veil on its true identity. The large-scale structure mapped by galaxy redshift surveys, gravitational lensing, and cosmic microwave background measurements leaves little doubt that dark matter dominates the mass budget of the universe, outweighing ordinary matter by more than 5-1. On the scale of galaxy clusters and superclusters, its gravitational influence shapes the orbits of galaxies, confines the hot intracluster gas, and determines the depth of the potential wells in which all baryonic matter resides. On smaller scales, its halos define the rotation curves of spirals, the velocity dispersions of ellipticals, and the survival of thin disks against tidal disruption. This ubiquity makes dark matter not just a background ingredient, but the principal architect of the cosmic web. A quiet irony lies in the fact that the same gravitational scaffolding responsible for the grandest patterns in the universe also governs the subtle kinematics of the faintest dwarf galaxies. Observations across these scales have been tested against high-resolution N-body simulations that evolve billions of particles under gravity alone, with results that match the observed connectivity, halo mass functions, and large-scale clustering of matter. The addition of baryonic physics, gas cooling, star formation, supernova feedback, and active galactic nuclei brings the simulations into even closer agreement with reality, though certain small-scale tensions remain. The core cusp discrepancy, where simulated halos have dense centers but observations sometimes suggest flatter cores, is one such puzzle. Another is the too-big-to-fail problem, where the most massive sub-halos in simulations seem too dense to host the faint satellites we see. These may be resolved through improved modeling of baryonic feedback, or they may hint at more complex dark matter physics such as self-interactions or a non-negligible thermal velocity dispersion. A lesser-known detail is that even tiny adjustments in the primordial power spectrum of density fluctuations, well within current observational uncertainties, can have measurable effects on halo abundance and substructure, making it difficult to disentangle astrophysical from particle physics explanations. The cosmic voids, though often treated as empty backdrops, also serve as sensitive laboratories for cosmology. Their shapes, alignments, and expansion histories depend on the balance between matter density and dark energy, and their low-density interiors are dominated almost entirely by dark matter. Galaxies in voids tend to be isolated and gas-rich, evolving slowly, their halos growing only modestly through minor mergers or smooth accretion. The dynamics at the void edges, where filaments converge, are strongly influenced by the surrounding dark matter distribution, pulling material out of the interiors and into denser regions. This flow, subtle on human timescales, sculpts the boundaries of the web over billions of years. Filaments themselves remain the connective tissue of the universe, their dark matter content far outweighing their visible traces. They deliver galaxies, gas, and smaller halos to clusters. Their geometry and density contrast, preserving the initial conditions from which they formed. Observationally, they are challenging to detect directly in dark matter, but weak lensing tomography has begun to map them in increasing detail, revealing their role as the structural framework of large-scale flows. The mystery of the dark matter particle continues to resist solution. Direct detection experiments operate in ultra-low background environments deep underground, searching for rare scattering events with nuclei, but the most sensitive detectors have yet to register an unambiguous signal. Indirect searches look for gamma rays, neutrinos, or antimatter produced by annihilation or decay, but astrophysical foregrounds make such signals difficult to interpret. Collider experiments search for missing energy events that could signal new weakly interacting particles, but no confirmed candidates have emerged. The irony here is that the cosmic evidence for dark matter is overwhelming and coherent across multiple, independent probes. Yet the particle itself has proven more elusive than many physicists expected when the search began in earnest decades ago. Meanwhile, cosmological observations continue to improve in precision. The combination of galaxy clustering, weak lensing, and cosmic microwave background data has pinned down the matter density parameter to within a few percent, leaving little room for alternative explanations that remove dark matter entirely. Modified gravity theories can mimic some effects but struggle to reproduce the full range of observations, especially in systems like the bullet cluster, where the separation of baryonic and gravitational mass is stark. A lesser-known observational success of the standard model is the match between predicted and observed halo bias, the degree to which dark matter halos cluster relative to the overall matter distribution across a wide range of masses and redshifts. This agreement suggests that the connection between luminous and dark matter on large scales is well understood, even if the particle nature of the dark component is not. As the universe continues its drift into a dark energy-dominated future, the structures defined by dark matter halos will become increasingly isolated. The inflow from filaments will cease, leaving clusters and groups as gravitational islands. Within these islands, the slow dance of mergers and tidal interactions will continue, but the overall architecture will remain fixed. In the deep future, only the galaxies bound within the same dark matter halo will remain visible to one another, while all others recede beyond the cosmological horizon. The quiet irony is that in such a universe, the evidence for dark matter's role in shaping the cosmos will still be written in the motions of the few galaxies that remain visible, even if the larger web has faded from view. In this way, dark matter's legacy is twofold. It has structured the universe we see today, and it will preserve that structure for as long as gravity can hold against the expansion. The fundamental question, what is dark matter, will persist until a direct detection or a breakthrough in theory provides the answer. Until then, its presence will be known only through the unbroken chain of gravitational effects that tie the earliest density fluctuations to the vast architecture of the present-day universe. The story of dark matter's influence on the cosmos narrows now to the precision mapping of its distribution and the subtle signatures it leaves in the motions of galaxies, the bending of light, and the statistical arrangement of structure. Surveys at optical, radio, and millimeter wavelengths continue to extend their reach, measuring both luminous traces and the gravitational imprint of the unseen mass. Weak gravitational lensing remains among the most direct probes, mapping the projected mass across cosmic time, while strong lensing offers detailed mass reconstructions in individual systems. In certain massive galaxy clusters, arcs and multiple images of background galaxies trace out the high-density cores of dark matter, revealing substructure down to scales of tens of kiloparsecs. These substructures, often devoid of significant baryonic content, match the predictions of cold dark matter simulations in number and scale, though their detection remains challenging. A quiet irony is that while these arcs and distortions are striking visual confirmations of gravitational physics, they represent only the most extreme tip of the vast dark matter distribution that pervades the space between them. On smaller scales, galactic rotation curves continue to be a fundamental test. High-resolution observations from radio telescopes tracking neutral hydrogen and from optical spectroscopy of stellar velocities allow astronomers to measure the mass profile of galaxies well beyond the luminous disk. In nearly every case, the results show that the visible matter alone cannot explain the observed motion. An extended dark matter halo is required. A lesser-known aspect of these studies is the use of low-surface brightness galaxies as especially clean tests. Their minimal baryonic content means that the gravitational signature of dark matter dominates, providing a clearer view of halo structure. Such galaxies often display slowly rising rotation curves, consistent with more chord density profiles, fueling ongoing debate about whether feedback processes or alternative dark matter models might be at play. In galaxy groups and clusters, the interplay between dark matter and baryons becomes more complex. The hot gas in clusters, observed in X-rays, traces the gravitational potential, but its distribution is shaped by both gravitational confinement and energetic feedback from supernovae and active galactic nuclei. Comparing the gas distribution to lensing-derived mass maps reveals offsets and asymmetries, particularly in merging systems. The Bullet cluster remains the most famous example, but many others show the same separation of dark and luminous mass during high-speed collisions, reinforcing the collisionless nature of dark matter. Simulations of these events reproduce the observed configurations when dark matter interacts only through gravity, placing tight limits on any additional self-interaction cross-section. The cosmic web's filaments, once active arteries of mass inflow, now act more as fossil structures, their density contrast frozen in commoving space by the accelerating expansion. Yet their influence endures. galaxies within filaments tend to be aligned with their long axes, a signature of the tidal fields generated by the surrounding dark matter. This alignment is also seen in the spins of dark matter halos themselves, an imprint of the anisotropic flows that built them. A lesser-known fact is that these alignments persist across a wide range of halo masses and environments, offering an additional observational check on simulations of large-scale structure. The mystery of the particle remains unsolved, but every measurement of the large-scale structure, from baryon acoustic oscillations to the shape of the matter-power spectrum, further constrains its properties. Cold dark matter continues to fit the data best, producing the observed hierarchy of structure from small halos to massive clusters. Warm dark matter models, with their suppression of small-scale power, struggle to match the observed abundance of low-mass galaxies, though some tensions on the smaller scales leave the door ajar for more complex scenarios. Axion-like particles, with masses so low that their quantum wave properties could affect structure on kiloparsec scales, remain an intriguing but as yet unconfirmed alternative. Direct searches for all these candidates continue in laboratories and in the sky, from shielded underground detectors to radio telescopes hunting for axion photon conversion signals in magnetic fields. Observational cosmology, meanwhile, keeps refining the cosmic inventory. About 27% of the universe's energy density is matter, of which only about 5% is ordinary baryons. The rest is dark matter. Dark energy makes up the remaining 68%, driving the acceleration that will eventually isolate bound systems from one another. The irony is that even as dark energy dictates the universe's future expansion, it does not erase the structures that dark matter has built. Rather, it preserves them in their final form. In the far future, galaxies bound together in clusters will still orbit within their shared dark matter halos, their mutual gravitational dance unaffected by the emptiness growing beyond their borders. At the scale of individual galaxies, the dark matter halo acts as both anchor and shield, holding stars and gas against tidal forces and external perturbations. At the scale of the cosmic web, it remains the connective tissue that has shaped the migration of matter for over 13 billion years. From the smallest dwarf galaxies to the most massive superclusters, the pattern is the same. Visible structures grow only within the invisible framework, and their histories cannot be understood without it. The legacy of dark matter in this late stage of cosmic evolution is thus twofold. First, it has determined the architecture of the cosmos with a precision that matches our most detailed simulations, confirming the gravitational paradigm on all scales we can measure. Second, it has resisted every attempt to identify its true nature, remaining an invisible but essential player in the universe's story. The quiet irony is that the most successful theory of cosmic structure we've ever built is one whose central component is still a mystery, its properties inferred entirely from the shapes, motions, and patterns of things it is not. Yet in this mystery lies the promise that future discovery could connect the smallest particle physics to the largest cosmic structures, closing a circle that began with faint ripples in the early universe and ends with the intricate web of matter stretched across the sky. In the final sweep of cosmic history as it can be traced from the earliest fluctuations to the present web of galaxies, dark matter's role is one of unwavering consistency, guiding the growth of structure from subatomic irregularities to the vast architecture spanning billions of light years. The first seeds, amplified during inflation, were invisible even in principle, yet their gravitational influence dictated where matter would gather and where it would not. Over cosmic time, those initial peaks in the density field became the nodes of the cosmic web, their filaments pulling gas, stars, and galaxies into the patterns now seen in surveys and simulations alike. Every stage of this transformation, from the collapse of the first halos to the merger of clusters, unfolded within the framework established by the invisible mass. By the present epoch, this web is both a relic and an active system. A relic in that its large-scale pattern was set billions of years ago. An active system in that matter still flows along its filaments and merges into its nodes. A quiet irony lies in the fact that even now, the motions of the most distant galaxies we can measure are still dictated by gravitational potentials sculpted before the first star formed. On the larger scales, the agreement between observation and the cold dark matter paradigm is striking. The spatial clustering of galaxies, the lensing patterns traced by millions of background galaxies, and the baryon acoustic oscillation scale imprinted in their distribution all confirm the same story. On smaller scales, the rotation of spiral galaxies, the velocity dispersions of ellipticals, and the survival of thin stellar disks in environments where tidal forces should be disruptive, all point to the stabilizing influence of massive, extended dark matter halos. A lesser-known fact is that even the intracluster light, the diffuse glow from stars stripped from galaxies during mergers, follows the distribution of dark matter rather than the hot gas, tracing the same gravitational scaffolding on intermediate scales. The particle itself, however, remains beyond reach. Decades of direct detection experiments have probed interaction cross-sections, down to levels that challenge many of the simplest models. Indirect searches in gamma rays and cosmic rays have placed strong limits on annihilation or decay rates, and collider experiments have yet to reveal a viable candidate. Alternative scenarios, self-interacting dark matter, ultralight axions, sterile neutrinos, remain on the table, but each faces its own observational hurdles. The irony here is that we know the total abundance of dark matter in the universe to within a few percent, yet we do not know its mass, spin, or interaction strengths. Its gravitational influence is measured in megaparsecs. Its microphysical identity remains hidden on subatomic scales. As cosmic time advances into the dark energy-dominated era, the inflow along filaments will continue to wane. Clusters will stop growing, their supply of new galaxies cut off by the accelerating expansion. The cosmic web will fade in physical density contrast beyond the boundaries of gravitationally bound regions, leaving isolated islands of matter adrift in an ever larger ocean of space. Inside these islands, dark matter halos will continue to shape the internal dynamics of galaxies and groups, preserving their structure long after star formation has ceased. In the far future, when the sky beyond the local supercluster has emptied of visible galaxies, any astronomers that remain will still be able to measure the mass of their own halo from the motions of its stars and gas. They will know, as we do now, that most of that mass is dark. A lesser-known implication of this accelerating isolation is that the evidence for dark matter's role in cosmic structure formation will become harder to reconstruct. Without the cosmic microwave background, without the large-scale galaxy distribution, and without gravitational lensing of distant sources, the clues will be fewer. The fossil record of halo structure and internal galaxy dynamics will be the primary means of inferring its existence. This is why the present epoch is a unique vantage point. We can see both the initial conditions in the afterglow of the Big Bang and the fully developed web in the modern universe, connecting them with simulations and theory into a coherent narrative. The quiet irony is that our understanding of dark matter's role is deepest at a time when its physical nature remains most mysterious. The same framework that explains the universe's structure also sets the boundary conditions for what we do not yet know. And so, the story closes not with resolution, but with the persistence of a question. What is the invisible mass that has shaped everything we see? It is a question that links cosmology to particle physics, that ties the fate of the largest bound systems to the properties of the smallest possible entities. Dark matter's influence is written in the arrangement of galaxies, in the smoothness of voids, in the coherence of filaments, and in the binding of clusters. It is in the stability of rotating disks, in the quiet survival of dwarf satellites, in the slow infall of galaxies toward their neighbours along invisible paths. It is in every gravitational lens that magnifies a background galaxy, in every discrepancy between visible mass and observed motion, in every simulation that reproduces the universe's structure only when it is included. This is the legacy of the unseen, a cosmos whose shape, history, and future are governed by something that does not shine, does not scatter light, and does not yield its identity willingly. From the first fluctuations to the final bound systems, dark matter is the constant presence, and while the luminous chapter of the universe may be brief on cosmic timescales, the invisible framework will endure, holding the remnants of galaxies and clusters in quiet orbits for trillions of years, long after the last star has faded. In the stillness beyond the telling, the motions slow. The long arcs of galaxies around their unseen centres stretch into intervals too vast to measure in human thought. Clusters, once fed by rivers of matter, now keep only what they hold, their boundaries calm against the expanding dark. Filaments remain as faint suggestions of a pattern drawn long ago, their substance unchanged, but their role now quiet, almost ceremonial. Inside halos, stars burn on in dwindling numbers, each one moving to the same ancient score, its path set not by the glow of neighbours, but by the deep pull of the invisible mass that surrounds it. No new grand structures rise. The scaffolding is complete. The voids between bound systems deepen, their edges receding past the reach of light. Over time, even the brightest galaxies will grow pale, their spiral arms fading into low-surface haze, their cores soft with old stars. Yet the halos will remain, still holding the shapes of what once was, still carrying the memory of the first ripples in the early universe. This is the lasting presence of dark matter, not an actor that enters or leaves the stage, but the quiet stage itself, unchanged as the lights dim and the scene empties. The clock of cosmic structure no longer counts forward in building and collapse, but in the long, slow drift toward equilibrium. The gravitational framework is at rest, its work complete, its form preserved for ages beyond counting. There is nothing to do but remain, to hold, to endure. And so the narrative fades here, not in a conclusion, but in a continuation without urgency. The galaxies abound, the clusters persist. The web, though no longer weaving, is still there in its entirety, a silent geometry against an ever-quieting sky. The observer withdraws, the scene lingers, and the universe rests in the shape that invisible hands have given it.